Now we're on to electric field and electric potential. Notes, this is part one that'll be in two parts. The space around a concentration of electric charge is different from how it would be if the charge were not there. If you walked by the charge, some of the electrostatic machine, a Van de Graaff generator, which we will be working with in class, for example, you can sense the charge. Hair on your body stands up. Just a tiny bit of it, you're more than a meter away, and more if you're closer. The space is said to contain a force field. The magnitude or strength of an electric field can be measured by its effect on charges located in the field. The direction of an electric field at any point by convection is the direction of the electric force on a small positive test charge placed on that point. This is important that we're working with positive charges. If you throw a ball upward, it follows a curved path due to interactions between the center of gravity of the ball and the earth. The centers of gravity are far apart, so this is an action at a distance. The concept of a force field explains how Earth can exert a force on things without touching them. The ball is in contact with the field at all the time. You can sense the force field that surrounds a charged Van de Graaff generator. You see that the Van de Graaff generator has all these negative charges around it, making your hair stand up, and we'll be doing this in class. An electric field is a force field that surrounds an electric charge or group of charges. A gravitational force field holds a satellite in orbit about a planet, and an electrical force field holds an electron in orbit around a proton. So here you have a planet and a satellite. This is the force of gravity holding it in. And if you had a proton, a positively charged proton in the middle, and a negatively charged electron, this electric field that would be around it holds them together. Like the picture I just drew, here's the electron, which is like the satellite. These would be the same right here, where the proton has a positive charge, this has a negative charge. This just deals with mass and mass. So this can be a repulsion and attraction. This is just attraction. Any electric field has both magnitude and direction. The magnitude can be measured by its effect on charges located in the field. Imagine a small positive test charge placed in an electric field. Where the force is greatest on the test charge, the field is strongest. Where the force on the test charge is weak, the field is small. The direction of an electric field at any point, by convention, is the direction of the electric force on a small positive test charge. If the charge that sets up the field is positive, the field points away from the charge. If the charge that sets up the field is negative, the field points towards the charge. How are magnitude and direction of electric field determined? You can use electric field lines, also called lines of force, to represent an electric field. Where the lines are further apart, the field is weaker. Since an electric field has both magnitude and direction, it is a vector quantity and can be represented by vectors. A negatively charged particle is surrounded by vectors that point towards the particle. For a positively charged particle, the vectors point away. Magnitude of the field is indicated by the vector length. The electric field is greater where the vectors are longer. You can use electric field lines to represent an electric field. Where the lines are further apart, the field is weaker. For an isolated charge, the lines extend to infinity. For two or more opposite charges, the lines emanate from a positive charge and terminate on a negative charge. So, in a vector representation of an electric field, the length of the vectors indicates the magnitude of the field. Since we said we use a positive test charge to check our fields, since we have a negative charge in the middle, they're all going to be attracted towards it. As you see, these are little lines, and the lines get longer the closer you get in. That means the field is weaker out here and stronger towards the center. In a lines of force representation, the distance between field lines indicates the magnitude. Here we're saying that it's all very strong as it goes around. This is the lines of force representation. The field lines around a single positive charge extend to infinity. What's saying is this one point, the field lines will point out from it because since this is a positive charge, the positive test charge will move away from it. For a pair of equal but opposite charges, the field lines emanate from the positive charge and terminate in the negative charge. See, since we use a positive charge to test this, everything's going to be moving towards the negative. All the arrows go towards the negative and away from the positive. And they will all go out from the positive into the negative, except if they're going the opposite direction, then they're going to be finding another. Field lines are evenly spaced between two oppositely charged capacitor lines. When you talk about a capacitor, which you have positives on one side and negatives on the other, that positive test charge is moving across to the negatives the whole time. You can demonstrate electric field patterns by using fine thread in an oil bath with charged conductors. The photo shows patterns for equal and opposite charges. If you look at that, it's kind of hard to see, but you'll see how the lines line up. You have a positive and negative charge there, and all the lines are coming up. You might be able to see this with iron fillings. Sometimes you'll see these on people's desks and stuff like that. Here's one with equal charges. You see it just scatters out everywhere. Oppositely charged. Here's an oppositely charged cylinder and plate. I know these are kind of hard to see, but they show you the field lines. Bits of thread suspended in an oil bath surround charged conductors line up end to end with the field lines. Oppositely charged parallel plates produce nearly parallel lines between the plates. Except near the ends, the fields between the plates has a constant strength. There is no electric field inside a charged cylinder. The conductor shields the space from the outside field. A beam of electrons is produced at one end of a glass tube and lights up a phosphorus screen at the other end. If the beam passes through the electric field of a pair of oppositely charged plates, it is deflected upward as shown. If the charges on the plates are reversed, in what direction will the beam reflect? Because if you see this electron beam, so it's a negative charge as it goes in, it's being pulled towards the positive charge, so it bends up and goes this way. So if we flip the charged plates and put the positive one on bottom and the negative one on top, when the charged plates is reversed, the electric field will be in the opposite direction, so the electric beam will be deflected upward. Can you represent an electric field? You can use it with the lines outward or inward vectors. If the charge on a conductor is not moving, the electric field inside the conductor is exactly zero. Big topic. When a car is struck by lightning, the occupant inside the car is completely safe. The electrons that shower down upon the car are mutually repelled and spread over the outer metal surface. It discharges when additional sparks lump to the ground. The electric fields inside the car practically cancel to zero. Inside the car, you're completely safe because it's all dispersing around the outside of the car. The absence of electric field with a conductor holding static charges is not an ability of an electric field to penetrate metals. Free electrons within the conductor can settle down and stop moving within the electric field as zero. The charge is arranged to ensure a zero field with the material. Consider a charged metal sphere. Because of repulsion, the electrons spread as far as possible uniformly over the surface. A positive test charge located exactly in the middle of the sphere would feel no force. The net force on a test charge would be zero. The electric field is also zero. Completely canceling will only occur anywhere inside the sphere. If the conductor is not spherical, the charge distribution will not be uniform, but the electric field inside the conductor is still zero. If there were an electric field inside a conductor, then free electrons inside the conductor would be set in motion. They would move to establish equilibrium, that is, all the electrons produce a zero field inside the conductor. There is no way to shield gravity, because gravity only attracts. Shielding electric fields, however, is quite simple. Surround yourself or whatever you wish to shield with a conducting surface. Put the surface in an electric field or whatever field strength. The free charges in the conducting surface will arrange on the surface of the conductor so the fields inside cancel. The metal-lined covered shields the internal electronic components from external electric fields. A metal cover shields the cable. So as you see all your wires and stuff, they are basically shielded. It is said that a gravitational field, unlike an electric field, cannot be shielded, but the gravitational field at the center of the Earth cancels to zero. Isn't this evidence that a gravitational field can be shielded? No, gravity can be canceled inside a planet or between planets, but it cannot be shielded. Shielding requires a combination of repelling and attractive forces, and gravity only attracts. How can you describe the electric field within a conductor holding a static charge? This is the end of Notes Part 1.